moving on to another application of market design for the common good, so staying on theme here, we will have the wonderful Alex Psomas from Purdue University talking about how to fairly allocate food.
Thanks. Can everyone see my screen and stuff? Yeah, everything's working great. Okay, awesome. Uh, I'm going to be talking about fair allocation of food. The problem here is food waste. I'll be resonating a lot of the things that were kind of in Yumi's and Alex's talk as well. So let me tell you very briefly about the problem. Food waste is a massive problem. Okay, so like the numbers are something like in the United States, 40% of the food in the food supply gets wasted. Okay. That is in the individual level, that's 1,000 apples per person. So, that's how much food gets wasted overall. If I threw 1,000 apples a year, and everyone in the United States did. In terms of dollars, that's $220 billion. In meals, I guess that would be 130 billion meals, which is more than 3 meals a person for everyone in the world. Or 10 times the world, I guess. No, almost. At the same time, you would think, oh, we're surely doing a wonderful job feeding everyone since we're throwing away so much food. You would be wrong. 35 million people in the United States are food insecure, 10 million of which are children. What I find as a very interesting number is this one. If I could circle, that would be great. But 100% of US counties have food insecurity. So, you would think that maybe, in Mountain View, a 3-bedroom house costs $4 million. Surely there's no food insecure person there. The answer is no. Surely somewhere middle of Indiana, that's mostly farms, there's no food insecure person. No, the answer is wrong as well. So 100% of US counties had food insecure people. Is there a question? Sure. No. So the question is, how should we allocate food? The message, I guess, of this talk is that what solutions sound reasonable really depends on the scale of the problem. So food insecurity and food waste are being targeted at very different scales, but typically NGOs. And they could be, at the city level, at the state level, at the country level. And, each of these organizations face very different problems in their operations, problems that kind of people in this call have something to say about. Economists, computer scientists, people with optimization expertise can help. But what solutions seem reasonable and are within the realm of things that they're interested in implementing, similar to what Alex and Ayumi said, depends on what the scale is, depending on what data you have. So let me kind of briefly walk you through some of my experiences with organizations across different scales. Okay, sorry, this slide is misleading. I haven't worked with everything here. These are just works that I'm aware of. Okay, so I'm aware of people that working with Feeding America. I'm aware of people working with the Food Bank of Southern Tier. I have worked with IHN. So let me briefly tell you about my experiences. So at the very, very end of the spectrum, the smallest scale would be something like the Ace Food Pantry at Purdue. Okay, so West Lafayette is 45,000 people and 50,000 students, and 15,000 faculty, so like 100,000 people. They have a pantry where people get points and they can go and purchase food with these points. The points get updated, I believe, every Sunday. Okay. The Ace Food Pantry is not interested in changing their pricing. They're not going to change that, no matter how much you convince them or how much of a better algorithm you might have. It's not even algorithmic. They've just converged these prices and that's it. They're not changing them. What they're interested in is donations. They just want more money. Okay. So it's not, even though they do have operations, they have a way of allocating food. They're not really interested in, fancier optimization methods. They just want cash. Okay. So that's the small scale organizations, those that work with this kind of scale of cities. The medium scale, so organizations that work in, big cities or at the state level, is kind of where most of the works that I'm aware of have had concrete impact. So let me tell you a problem of an organization I work with, IHN, the problem they had and kind of what we brought to the table. And this is kind of similar to what other organizations face in this level of scale. So here's how one of the programs IHN runs worked. So IHN is the Indie Hunger Network. Their program Food Drop worked as follows. You have these truck drivers who, were supposed to deliver, 100 pounds of broccoli to Walgreens. And they show up late. So Walgreens like, I don't want this food anymore. The food is still pretty edible, but, Walgreens won't take it. Or, the top pallet shifted. So they open the truck. They're like, oh, this is, it's one pallet out of 8. The other 7 are fine, but they still don't want it. They just reject it on site. So now this truck driver, has a bunch of food. The outside option is to go to a landfill and drop it off. And IHN, this program is trying to prevent that from happening. So the way the program would kind of run is that the truck driver, the donor, would contact IHN and tell them, here's what happened, here's the food, here's how much food, here's where I am, here's what's happening. IHN would identify a recipient, they would facilitate the exchange of information, and then the driver would go and drop off the food. Okay. Now, in our involvement in this process, IHN had a very concrete goal. The person running this did not want to run this anymore. They were doing too much. They just wanted to remove all humans from the loop and just completely automate this. Okay, so complete free reign of what we were going to do. Do anything you want. We just want this to run by itself. Okay, this was the goal. Completely automate it. So now when we're talking about automation, we're talking about algorithms for matching really donors to recipient. This is kind of things that the people like us are very familiar with. Okay, so we're interested in designing an algorithm with fairness and efficiency guarantees. Okay, so how do we model this problem? For the longest time, I thought this is how we're going to model it. I mean, this is because I had work in the area before my involvement in this process, but here's a concrete model that one can think of a problem like this. You have n agents, you have t indivisible items. Agent I has some value VIT for item t. Agents A have additive preferences for simplicity. So this is, the most standard fair division kind of model. The twist is, of course, a standard online twist that items arrive over time. So one item per each stage for t stages. You learn the value of the item when the item arrives. Okay. So the first instantiation of this model is actually by work by Alexandrov et al. In EC'25 2015 that was about food donations, by the way. So this is a pretty fundamental, theoretical problem. You don't have to model food allocation with it. You can model all sorts of, allocations with this model. There is a modeling decision to be made, which is how are the values generated? And as it turns out, in terms of the theory, the answer really matters. So if you're thinking of an adaptive or an oblivious adversary, standard worst case analysis, or if you think of a Bayesian adversary, so values are drawn stochastically, the answer is very different. And there's, a whole jungle of results here that, many people have contributed to. So, at this point of my involvement, I was pretty confident that one of these algorithms would be the solution to IHN's problem. Specifically, I was thinking of this one. This is a joint work with Herdis Benade, Alex Kazaskov, Ariel Procaccia, and David Zenk. And the first kind of draft of what we made was using this specific algorithm that I'm not going to discuss. But there's a complication in the model. The model does not perfectly reflect reality. So I guess the second message of this talk is not, the first message is that scale matters. The second message is sometimes you need a really specialized model to do a good job. A model that, perhaps is not of interest outside of the very specific application. So here's a complication that we run into. You have this truck driver that is in Gary, Indiana. That's where their food got rejected. And they were going to head out to Kokomo over here. If everything went well, and if, Walgreens, whoever, Whole Foods, Target whoever accepted the food, that was their next destination. The food got rejected. Okay, so now they want to donate it somewhere. And there's food banks over here, south of Gary, over here in Lafayette, and a couple, say, for simplicity, near Indianapolis. The problem is that these two are too far. Okay, so some recipients require too much additional driving. Okay, so even though food does not have preferences, as it turns out, drivers have preferences. And we're interested in having them use the system, so we need to keep them somewhat happy. For the longest time, I thought that we could model this by just zeroing out the utilities, but and we'll see how this does. But at the end of the day, we have a choice. We can have some heuristics based on the existing theory that we understand very well, or we can build some new theory. So let me very quickly tell you about the new theory. This was an EC paper from last year. So the model that actually informed the decision of the algorithm is graph-based. So we have a graph. The nodes correspond to locations. Some of these nodes have food banks. Edges naturally have weights that are the distances between locations, and every node has some food insecure population. Okay. So drivers, not food, arrives over time. A driver arrives, one per round for a total of 3 rounds. Drivers appear in some random node. Their destination is some random node. And they have a value that's stochastic. That's the value of the food they carry. Okay, so that's the model. And drivers must be matched immediately and irrevocably. So here I'm not only interested in fairness. Fairness would be that the food banks receive, equal food. But also I want to be efficient with respect to the drivers. I want to say that the drivers don't drive too much. Okay. Again, I'm skipping. I'm doing things fairly quickly. So what's the algorithm that we're actually running right now? At each round T, so every time we get a donation, we find the food bank that's closest and to the origin, to where the driver is, and closest to the destination, to where the driver is going, and we're allocating to the better of the two. Okay, better by value divided by population. So this is some proxy of the value of doing this match. Okay. And the theorem is that, if under some technical condition, this is 3 driver efficient, so no driver is doing more than 3 times the work, and basically envy-free in the limit. Okay. By the way, this joint work with my students Marios and Partosh. Partosh is in the postdoc job market, so please hire him. But let me briefly show you some experiments. Algorithm 1 is this algorithm we're running. Greedy with cutoff is what we wanted to do initially. So this is the thing you would have come up with by fudging the theory in the first version of the model. And so this top table is for Indiana. If you look at these very closely, every number is better for greedy with cutoff. So heuristics are marginally better for Indiana. So what's the point of theory? The point of theory is that if you try to run this in California, it would run horribly. Okay. So, so in a sense, theory buys you the robustness. You don't have to guess.
How bad is it to have? I mean, I'm looking at some of these and they look kind of really close to each other. I mean, between 1.00025 and 1.0002, it's like,
Are you talking about
are
the
we
top
talking
table or the
about
bottom table?
meaningful differences?
Sorry, are you talking about the top or the bottom?
Actually, let's start with the top table.
The top table.
The top table, let's say,
Yeah,
because
yeah,
the
they're
top
very
table really
close.
the difference.
But yeah, things are close.
At
But
least on
but
envy.
Indiana is small. Sorry, what was the question?
Oh, I'm saying, like, how meaningful is it to talk about these kinds of differences when we're talking about things that are like, errors on what, like the third or fourth bits, kind of like
Sure,
of
sure.
a
Of
way
course,
of
of
like
course, of
the
course. course. But I'm saying I can't just say I can just show, similar to Alex, this like slam dunk, like oh, heuristics were terrible, like, and we're doing awesome. Heuristics were pretty
It
good.
would have been nice to see much better numbers. I agree. I mean,
Yeah.
it's interesting regardless, right? So, like, it's I think,
Yeah.
but yeah.
But the theory gets you the robustness. Like you can implement this in a different state, and that brings my next point, and be fairly sure things will work out. So what's the status of this? The status is that this is actually running. The project moved from IHN, who was a phenomenal collaborator, to Society of St. Andrews. And currently, we're trying to improve some features, so we're not quite seeing the traffic we would like versus what was when a human picked up the phone. So we're currently trying to implement a voice to text instead of filling out a form. We're trying to advertise. We're trying to extend to a different state. I mean, we're trying to extend to a nearby state, but also we're trying to launch this somewhere in the state of Washington. And this is kind of another huge bonus of having an automated system. That expanding is free. We just need to set up Amazon AWS, like that's and Twilio, which is the texting service. It's like very, very easy to relaunch if you have everything already out there, open sourced. Okay, so this is kind of one of my experiences with organization at this level. I think I might very quickly, kind of skip this, but I've worked with another organization in Pittsburgh when I was a postdoc for 1-2 Food Rescue. Their problem was identical. You have donations, recipients, you want to do the matching, but I want to quickly mention they did not want an automated matching system. They wanted a recommendation system. They wanted us to recommend the recipient. They didn't want us to decide the recipient. And they wanted, a transparent display of the reasoning. So very different than, straight up doing optimization, the things we're good at. Okay. So the thing we ended up building for them is something like this. A donation arrives and we recommend, green fire, pretend, and these are the reasons. So we bring this nice interface for them to use. This was a major project with a lot of people. Min Kyung Lee, who is an HCI expert, was kind of at the head of this, at the interface of this collaboration. The status is completely unknown. Okay, so we built this pilot after much effort. 412 was pretty slow and unresponsive in parts, and then COVID happened, and then randomly, late 2022, December 2022, we had this email of like, we might launch this. Okay, and now no one knows what's happening. Okay, so the last message is you need a good collaborator. Okay. So that's kind of all I wanted to say for the medium scale. In terms of large scale, I'm aware of some works that are wonderful. For example, Prendergast in a few years old paper discusses how they switched the operations of Feeding America using now a market kind of solution using artificial currencies. And there's a lot of work kind of from our community about analyzing artificial currencies. Another paper by Bernadette discusses another kind of very large organization that works across all 50 states. And they also, similar to the Prendergast paper, kind of stress this point, and this is the last point I'll be making, which is at that scale, the most important thing is to minimize the disruption you make. So when you propose a solution, you can't just like do whatever you want. At that scale, things can only change a little bit. Um, uh, so different scales require different solutions, and that's all I had. I'm a little over, I think. Shoot. Thanks.
Thank you, Alex. Yeah, I think that I am next. So
Yes.
give me a second. Um, yes, continue to share. What? Okay. Um, I thank you everybody for listening. My name is Yair, and I'm going to talk about a relatively old project, but it was a really fun project, and it was the first time that I actually worked on a problem of like practical implementation of a fair division problem, right? And So this was a project that I was doing, you see, like Alex, as a postdoc with Ariel Prokacha. There might be a connecting thread there. And back in 2016. And um, maybe what I would try to do here is to tell you a little bit about my own very small experience about how to be effective about approaching these problems, because I tried to do this later as well with a kind of mixed degrees of success. Some of the projects were successful, some of them less. Perhaps we'll talk about this. So the first step, I think, is to identify a problem that has really nice properties. So I think that we had several good examples. I think that Alex and Alex were showing us problems that are just objectively important, right? You know, it's really important for us to solve food insecurity. It's really important for us to solve refugee problems in the world. I think that, I mean, while it is important to solve spousal disputes, I would say that kind of like, you know, it's not, a human's problem is not like consequential in that way, but it is a very common problem, right? And I think that that's why it's so appealing, right? Because we encounter it on a day-to-day basis, right? We have chores, we need to do them. And I think that in that sense, rent division is also that sort of problem, right? It's a really common problem that most adults have dealt with at some point in their lives, right? Like just sharing an apartment with roommates. And the way that the problem is modeled is that we have three agents in this case, and we have three rooms, right? So we have blue, green, and orange rooms, and the numbers that you're seeing here are just how much does each one of these people value the room, right? So think about this as how much rent is this person willing to pay for this room. All right, so Alice is willing to pay $854 a month to stay in the blue room, $2,403 to stay in the green room, and $2,743 to stay in the orange room. Right, and the reason that these numbers are so weird is because they come from an original instance that came from Split It. And then our job is to find a way of assigning the rooms to our roommates and to decide on a level of rent or on a division of the rent of the $6,000 a month rent here to divide it in some reasonable way amongst the rooms, so that first of all the sum of the payments is the total rent, and that it satisfies certain desirable properties. Right, so just kind of like to start us off to understand the problem a little bit. So first of all, I want you to observe that, I mean, you can verify this, that all of these numbers, like all of the tenants' valuations for the rooms sum up to 6,000 exactly. So you can think about this as the tenants proposing, how do they think the rent should be divided, right? And similarly, the total rent, as I said, that is assigned is it sums up. So the total 896 plus 2,382 plus 2,722, all of that sums up to exactly the total rent of 6,000. Another thing that you can observe here is that each one of the tenants in this case got the room that that kind of like each room got the tenant that values it the most, right? So this assignment is also socially optimal. And this is actually not incidental. This will actually be guaranteed, but we'll get to that in a second. All right. So why is this a good problem, in my opinion? I think that it's a really common problem, right? All of us, as I said, kind of had to deal with roommates at some point. It has a really expressive and simple formulation, right? So we all kind of like, it doesn't require somebody who is a theoretical economist or a hardcore CS person to get a good grasp of this problem and its parameters, right? So it's kind of nice. You can talk about it, like you can have informative and fun discussions about rent division with a non-expert, right? And it's also really nice and easy to analyze and produce solutions. And also, and perhaps more importantly, it's easy to generalize. So this work came out in 2016, 17. There were a lot of really nice and interesting works following it. Some of it that came from Ariel, some of it that came from other researchers. Rodrigo Velez that worked on fair division with budget caps, robust fair division. There's so many other variations of this problem that are all interesting and fun to work on. So one of the other things that I think is really important when you're working on a practical problem is to make it accessible. Okay, so I was lucky enough to come into this project when the Splitit website was already online. It was kind of recently online when I joined. And it offered all of these applications, right? So dividing grant, dividing taxi fare, dividing academic credit, dividing items, and dividing tasks, right? So we had this really nice interface, nice, clean to work with. It's still up. And it's easy to interact with, it's pleasing on the eye, and that I think is also super important. Because what happened is because I think the interface was so nice and because the problem was so natural, it received a lot of outreach. So there was just that year in 2015, there was a New York Times article about rent division and the automated fair division. They were talking about two calculators that were kind of out. One that was based on a Sperner's lemma kind of argument, and then there was split it. But because of that article, there was a really huge boost in the amount of data that was collected, right? So when we started our study, there was already more than 13,000 users. So by the 13,000 users, there was actually more, but like 13,000 that were usable users, that were like legitimate interactions with the website, as opposed to like people just playing with it. And ever since, of course, there were many more. Um, and as I mentioned, it was later also modified and extended. Right. So let's just, so that we are all on the same page, let's understand what the model here is exactly. So we have agents and we have items, right? Where the items are just rooms, and each one of the agents has a utility, like a value for each one of the rooms. Okay, so we have each agent just reports how much they value each room. We added the requirement that the valuations have to add up to the rent to normalize them. It's not a strict requirement like for this to work out, but this was just done so that it would be a little bit more easy to for people to reason about this model. And each one of the agents has that, right? So each one of the agents has this value. So each edge here kind of represents the weight or the value that each agent assigns to each one of these items. And our job is to come up with an assignment of agents to the rooms, right? So each agent receives exactly one room, and with a pricing scheme. So the prices are to each room. So P1 to room 1, P2 to room 2, P3 to room 3. And the requirement is that the prices all add up to the rent. Okay, so that is a hard requirement. We have to cover the rent. Like the landlord doesn't care like how we divide the rooms or how much each room gets charged. They just look at the check at the end of the month and they want to make sure that the rent is covered, okay? I want to say as an aside that it is not necessary actually for the prices to be non-negative, okay? So it could be the case in this setting that you actually have to pay somebody to stay in a certain room. And in some real world instances, this happened, right? So there was one instance that was this really large house, I guess. I mean, we only get to see like the agent's valuations and like what they call the rooms. Okay, so they give the rooms names and then they evaluate. And one of the rooms was called something like small underneath the staircase. So imagine, I don't know, like Harry Potter or something like that. And that room received a negative price. So basically, whoever lived in the small room, and like it was essentially a converted closet that they put a bed in or something. And whoever lived there actually, according to the split rent calculator, should have been paid to stay there. So yeah, that I guess sends a signal more to the landlord that they should probably come up with less crappy rooms. But yeah. Okay. Any
But
questions so far? Are we good? Yes.
yeah, about negative price. If there's a negative price, isn't it better to kick the tenant out and just have two roommates and
Yes, yes, it
Mm.
is better. That again, it sends a signal mostly to the landlord that the rooms that they're offering are just, some of them at least, are just objectively terrible. So yes, exactly that.
that's not a
You
stable,
are, that's the thing. Yeah,
Uh,
that's exactly what the landlord should do. Yeah.
so one more question. I was gonna wait with asking about incentives, but like if they're the kind of yeah if people are bidding so that the price is negative, does that say there's something wrong with maybe it's not strategy proof and that's why they're bidding
Th-
negative?
This is definitely not a fair, this is definitely not strategy proof. There is no, like, it's actually pretty easy to see that, to show, like, this is like one of the homework exercises I give students in my class to prove that there exist instances where no envy-free, like no reasonable allocation has, is truthful. Like
But
there is
is
no,
this a concern in practice? Because I remember when I was in this situation, is the two people they're gonna be my best friends in a few months, but right now they're strangers, and you know, I want to pay as little rent as I.
I agree with you. It's not ideal. I mean, yes, you are right. There are incentive issues. There is no reason. I mean, because strategy proofness is kind of fundamentally incompatible with really basic properties, like, even just allocative efficiency and stuff like that. Then it's really going to be hard to come up with some mechanism that is that satisfies it. So we just didn't go in that direction in this study. I mean, it's not. Yeah, although I do agree with you that it is important, right? In this situation, right? So an outcome here is essentially some kind of an assignment sigma of the rooms to the agents, right? So this on the left here, that's sigma, and the price vector p, right? So this is this, and we say that it's envy-free. Basically, if every person values their own assignment more than any other room, right? So here the underlying assumption is that when agents evaluate the room, they look at the utility that they get from the room, and they just deduct the price, right? So it's just the utility for the room minus the price. That's your utility from this outcome. Okay, and this statement here just says that for any other room, if I look at my own assignment, I weakly prefer it to any other room. Okay, so I prefer my room to any other room, given the current pricing. Make sense? So the good news is that we can actually compute these things pretty easily. Okay, so we can easily compute an envy-free allocation, and in fact, it's a special case of competitive equilibrium when agents have what's called unit demand valuations. Right, so it's actually a really nice thing, because that means, first of all, that if the allocation, if the outcome that we came up with is envy-free, then the room allocation is optimal. Okay, so it maximizes utilitarian welfare, so it's kind of nice in that way, right? So each room goes to the person who likes it the most. And the second welfare theorem says, I mean, these statements are for much more general cases, but we're just using this very specific instance. The second welfare theorem says that the actual underlying allocation doesn't matter very much, as long as you're choosing one that is maximizes welfare. So basically, if one outcome, right, is a competitive equilibrium, it's envy-free, then under the same price vector, any other a room allocation that maximizes welfare will also be envy-free. So we're fine. Okay. Now, why is this helpful? Well, it's helpful because it tells us that, okay, all you need to do is first compute an optimal allocation of the rooms to the tenants. Okay, so just compute an optimal allocation. Just do like maximal weighted matching or whatever your favorite algorithm is. Okay, and then find an envy-free price vector, and you can use just a linear program to do that. Okay, so it's a linear feasibility program. It's pretty straightforward, especially when there's like 3 or 4 tenants. So it's a really easy problem. Okay, so we can just ignore the actual room allocation, just assume without loss of generality that that room 1 goes to agent 1, agent 2 gets a room 2, and so on and so forth. So that's pretty easy. Okay, and then it just leaves us with this interesting problem of which envy-free price vector we want to choose. Okay, so let me give you an example of what I mean by that. Okay, so let's assume that our agents have this really straightforward instance. Okay, so we have a rent division problem where all of the rent is $1,000, and each person is really single-minded. Okay, so Alice just wants the first room, Bob wants the second room, and Claire wants the third room, and values like each agent just values them. So they're not competing at all over the rooms. There's like really great. Okay, so what are NV3 allocations here? Like what are the NV3 rather price vectors here, according to our definition? All of them, right? I'm assuming that this is a triangle alone, like what you are doing there with your thing. Yes, all of them. Yes, correct. All of them will be NV3, right? So in fact, so we assign the rooms in the right way, and intuitively would want to say, look, in this situation, we should equally split the rent, right? That's like the right thing to do. But this is also NV3, right? Just Alice pays all of the rent. Alice's utility will be zero, and everybody else but the utility for any other room is zero too. So like she's fine, and everybody else is of course ecstatic because they're not paying any rent. So that's not great. Okay. So and you would say like, okay, this is kind of esoteric, but originally Split was implementing a mechanism that the way it kind of worked is that it picked a victim, like a room, and then just increased its rent until like some threshold condition was met, and then continued on to another one. So it kind of iteratively increased the rooms and the rooms prices until it reached an equilibrium. And that kind of technique would result in something like this. Right, it created not, I mean, these kinds of extreme instances did not get fed into Split, but like semi-extreme instances were fed, and then there would be a real imbalance in the rent, and people did email and complain about it. Okay, so then it made sense to talk about, okay, so we want to come up with some kind of an optimization metric or some kind of a fairness metric over the price vectors, right? So kind of finding of the NV3, of the really nice, well-behaved price vectors, the NV3 ones, we want to find ones that satisfy certain nice properties, okay? And then we looked at two like metrics. One of them were disparity, okay? So disparity is essentially how much difference is there, what is the maximal difference between the utility of any two tenants. And here notice UIP is just the utility that I have for my room minus the price that I'm paying. Okay, so that's the way I compute utility. So I just take the differences between these two, and then I just want to minimize rather the maximal disparity. Okay, and then and while ensuring that the price vector is NV free. Okay, so that's like a linear program that tries to minimize this gap. Okay, between like the red agent's utility and the blue agent's utility. The other objective is the maximin objective, right? Which just says, look, let's look at the saddest person here. Okay, so the person who has the minimal utility, and I'm going to try to maximize the utility of the minimal utility agent. Okay, such that again, the price vector is NV3. Okay, so essentially I want to just maximize the height of this bar. Okay, make sense? And what's nice in this setup is that we don't really have to choose. Okay, we have a theorem. I'm going to be very brief. We have a theorem that just says that the maximum price vector is unique and it's also equitable. It minimizes the disparity. Okay, but this is not an if and only if. Like there are price vectors that are minimize disparity but are not maximin. Actually, in real life, we split it instances, so that was pretty cute. Now, what's interesting about this study, okay, so all of this stuff, I mean, it's pretty kind of like not, let's say, the most deep theory ever, right? But it's actually really nice because we can show that it works in practice. Again, because we had this data set from Split It, right? We could do an empirical study. Okay, we can look at all of the real Split It instances. At that time, again, it was like 13,000 instances, and measure like, is the maximum solution actually solving stuff? Like, is it improving things? Or maybe the original solution was fine. And what we could show is that, yes, the improvement in disparity was something in the order of like, for 2-room instances, something like 11% on average, 8% on average for 3, and 5% on average in 4, and overall like a 9% improvement. And in terms of the maximum, so like utility, the utility of the lowest person, we got an overall 4% improvement. And that's not kind of like looking like a ton, but if you're talking about monthly rent, that actually adds up to not a little bit. Okay? Now, we actually went a step further. And because there was that New York Times article that came out and there was a lot of people that were interested, we actually went ahead and did a user study, which was really annoying to do. But we did it. It was exciting. And we got like we emailed there was like a little bit of like a rush because we need to get an IRB and we needed to kind of get everything settled, and we sent out these emails. We offered people $10 back in 2016. You could buy a house with it. No, I'm kidding. It was but it was it was it was a lot of money, I think. Maybe not enough because we got 46 responses total, but it was pretty good. I mean, actually 46 was enough for our purposes. Okay, and we basically sent them out a survey. Okay, we asked them how much do you like the current allocation versus what split it gave you, like the maximum solution versus what split it gave you, and people were actually quite happy about it, right? And I think that that was actually like I think for me at least this is the main lesson, and this is something I really want to implement in a larger scale. Is how do we get information about how people like our solutions, right? Does it matter, right? Because maybe people don't really care about this chore division stuff, or maybe they don't care about food drops, or maybe like it doesn't improve. And the only way to do it is really by asking people in a large scale. And it's really, I think, the most important thing. So for us, I mean, I'm just going to finish here to show that yes, indeed, people really, really liked our solution much better than the original NV-free calculator solution, right? So they gave it an average ratings of like 4.2 or 4.15, depending on the question. And it was actually really, really useful. And I was pretty pleased about that. But right, I think that this is a good time to stop because I do want to hear, very much want to hear what Aviad has to say about course allocation. I also wanted to talk about course allocation, but I figured that it would be stupid to have two talks about it. So I would want to hear what Aviad has to say. So thank you very much, everyone.
Thanks, Yair. Yeah, so our last speaker, Aviad Rubinstein, assistant professor at Stanford, associate professor at Stanford. Aviad, your assistant, sorry.
Still assistant, hopefully
Okay.
associate.
Your website is updated in I don't know 2020 or something. Yeah, so Aviad will talk to us about course allocation. We're very, very happy to have him.
Trying to turn on the share screen. Thanks, Alex and Yair, for organizing this wonderful workshop. Yeah, so okay, I'll talk about course allocation a little bit, but so on the left you see my co-author Eric driving his Honda, or the photoshopped a little bit into driving a Honda. And on the right, you see my neighbor, Muhammad. Muhammad actually moved to a nicer neighborhood now, but and my colleague, Muhammad, he's sitting on his Porsche. And I want to ask you whether you think Eric would trade his Honda for Muhammad's Porsche. But I'll keep you in suspense about this question. Actually, this is very relevant to what you just told us about, but I'll keep you in suspense because I want to tell you a little bit about courses, and I'll come back to this question later. So this is some stuff about course allocation. Kind of the middle part of this talk is about an EC'25 paper, joint work with Eric Buddhist, Wei Chen Gao, Abe Othman, and Chanfan Zhang. And Ruchuan and Chanfan were actually undergrads for most of the collaboration. Now they're third-year PhD students. Officially at Stanford and Princeton, although they're both here right now. Chanfan is visiting. Good. So background and course allocation. This is a Stanford Daily, our student newspaper, and here are some headlines about like how the Stanford used to use this like kind of first come first serve system for signing up for classes, and of course the system kept crashing because everyone wanted to sign in exactly the same time. And then they switched to this other system, batch and roll, and you see students were maybe not so happy about this one either. This is not only a problem at Stanford, this is some Reddit thread about how stressful signing up for classes is. This is the newspaper at Texas A&M. This is panic surrounding course registration. And this is some clickbaity title inside higher ed. I didn't buy the bait, so I don't know what actually happened to the student bot. But okay, I do want to mention that when I started working in course location, I thought, I have a undergrad in math and the rest of the degrees are in computer science. I took a bunch of lecture-based classes, or basically uncapped in other like MBA law schools. The classes are capped because they have like discussion base, and like when I talk about this to like law students or MBA students, are like, this is like a career path changing, like a huge deal. And so like we have this kind of limited resource, and I want to allocate to students. And before we do this, we want to model this. So here's the kind of standard-ish model in the literature, is each student has preference over schedules or bundles of classes. And I want to highlight that these are really combinatorial, like this is really combinatorial demand, like the kind of, it's not like some really nice additive. In practice, you can kind of go with, you're okay with additive preferences as long as you also allow for complex constraints. For example, you can take two classes at the same time, or you need at least some number of units, or at most some number of units, etc. And it's okay if it's a reasonable kind of compromise to think of the additive preferences are private and the constraints are public. They're kind of given by the registrar's office or the degree program. Each class, each class has a capacity, and the assignment is indivisible. That's also very important. Good question so far? Okay, so let me tell you about kind of some outdated solutions. I want to say these are things that people used to do, but we still do them. So one kind of approach is serial dictatorship. You can just order the students. For example, at Stanford, we used to have like a first come, first serve. So rank the students by how fast their internet connection is, or their bot that signs up for classes is. And then just let students pick from whatever is left. When I was an undergrad at Technion, it was done by seniority. So they look at like how many credit unions you've accumulated, and you're ranked by that. Last time I checked, they still use this. Now at Stanford, they use a mix of first come, first serve, and seniority. And as you saw, it still has a mixed, students still have a mixed opinion about this. So what we like about serial dictatorship, it's strategy proof and Pareto optimal, but it's really not fair. So, if you're doing like a housing
Aviad,
allocation, room assignment, right? Like someone always going to get a better room.
Aviad,
But yeah, I
by
don't have a question.
what exactly you mean serial dictatorship? Like you choosing the entire bundle of courses
Yeah,
for.
so it's you have, so like when I was at Technion, you have like a 15-minute window. You log in when it's your turn. You see what classes are available. You sign up for whatever class you want, and yeah, or at Stanford, it's like first come first serve. So you sign up for whatever class that you want, and then there's actually some gaming because if you sign up for really highly contested classes, then it's more likely that the server will just return an error, and then you have to kind of wait in line until you have to wait until the next time the server is going to crash, is going to return an error on your request, and it's going to crash, and then a bunch of students are going to kind of pass you. Anyway, but in theory, it's strategy proof. At optimal, it's really serial dictatorship is really unfair. The top data dictator is getting all their favorite classes, and actually, students at Stanford said they're not just getting all their favorite classes; they're actually shopping for classes. So they're like they can sign up for like 20 units of like fun electives that they're shopping for, and they get take like the best try all the wine tasting classes, while most students don't get any. So we would like to at least satisfy something like NBA free up to one good, EF1. Okay, another so single dictatorship strategy prepared optimal but not fair. Another option is like a fake money auction. So this was used in my master's program at Tel Aviv University. Again, last time I checked, it's still used. Every student gets a budget of 100 points, and you can bid in the various classes. But okay, why are you using an all pay auction, which is like it's really far from strategy proof? So you can think about it. if I bid like $1 million on a house, and someone else, this is a kind of, I live in San Francisco Bay Area, so someone else is going to outbid me if I bid only $1 million in a two-bedroom apartment, and I'm going to lose the auction, but at least I get to keep the money. But if I bid with fake money, bid 60 points for the algorithms class and someone else bid 65 points, I get to keep my fake money, right? So it's like an OP auction. I have this budget that I can split between classes, but what I don't get, what the class I don't get, the budget is wasted. And bidding in an OP auction is really hard because um, if there's something you want to win, you have to like really bid high to make sure you win. If you don't think you might lose it, you should bid zero to not waste any of your budget. So it's really not strategy proof. It's also difficult to express complex preferences, like I want to take either one of those two classes that overlap in the same time and satisfy the same degree requirements. That being said, as far as I know, it's still used.
I mean,
There,
there are
so
always in the
yeah.
just as a comment about the losing fake money. When I was a faculty at the National University of Singapore, and there, what they would do is they would let you keep the points. So then,
Oh, okay, yeah. Keeping the points is very interesting. It has some really complicated. Now you have to strategizing is very complicated. I'll get back to that at the very
for
end.
sure, for sure.
The very end of the talk. There is something called Harvard Business School mechanism. Basically, you do a simultaneousship for one class, and then you go back in the reverse order, and it's like a snaking order. It has some. It's better than the serial dictatorship, but has poor incentives. Don't want to spend much time about it. I just want to say, yeah, it's has some serious issues. Last time I gave a talk at Harvard, they're still using. They checked and said they're still using it, and they spend like some enormous amount of effort trying to explain this mechanism to students. Good. So this is kind of background about outdated solutions that are still used in practice. Let me tell you about the state of the art, which is uh, um, equilibrium based. So competitive equilibrium from equal incomes. So students are submitting to this centralized system their preferences over classes, and the system spits out like a pair of prices and location, and it has to satisfy a competitive equilibrium condition. So every class is either full or zero price and under demanded. So if it's like an uncapped class, we can just keep the price zero and just keep it under demanded. And every student is allocated the favorite schedule given the prices and budget constraint. So this solution is much better. Unfortunately, it often doesn't exist because we have indivisible goods and combinatorial demand. So what Eric Budish proposed is this approximate competitive equilibrium for equal incomes. Very hard to pronounce. So there is each agent is given some budget that's not exactly the same, but approximately the same. And maybe we're not exactly filling the classes, but the kind of playing around with the capacity a little bit. So it always exists for some good parameters. In particular, the budget inequality can just be a tie-breaking, like arbitrarily small budget inequality. It satisfies a strategy proof in large. As the market kind of is large, it's approximately strategy proof. It's Pareto optimal up to this clearing error, envy-free up to one class. But we need an algorithm for finding this equilibrium, right? Because we actually want to output the allocation. So Eric Budish proved that it always exists, but we want to find an algorithm. And in theory, as a PhD student, I had a lot of fun proving that it's really, really hard to approximate, maybe even harder, assuming some conjecture. In practice, there was a heuristic algorithm used in practice. There's a startup called Cognimus, several MBA law programs. This is a medium-sized instance, so it's not Facebook-sized graph, but also large enough that you cannot just brute force. And algorithm originally took a few days with significant compute power, but maybe a few days is okay if you only do this once every semester. Okay, so we had this EC'23 paper. I want to tell you kind of briefly about kind of like a couple of things that we found. So one thing is we found just a much better, faster heuristic algorithm. So the blue line is kind of the convergence rate for the kind of previous commercial state of the art. You can see after 4 hours, it's still not quite converging, while the green line is ours, it converges in less than a minute. So way much faster. And okay, so we get better allocations faster. And schools can now, because it can run it so fast, it can actually interact, and you can try something, and now it say, okay, no, what if I ask Alex to teach another class? Would the students be happier, and how much happier would students be? You can kind of try that. And also, we have the first empirical analysis of ACI incentives on real instances. But why do we need to analyze incentives? It's strategy proof in large, right? So like as the number of students goes to infinity, it's approximately strategy proof. So I opened a paper that proves that it's strategy proof in large, and there's a caveat which, for the theory to kick in, you need large to be very large. So you need this number of students to be much larger than number of classes, actually much larger than exponential in number of classes, actually much larger than doubly exponential in number of classes. And only then this kind of theory of strategy proof in large even begins to kick in. So it was kind of relevant to kind of try this in practical. Are there practical manipulations? We didn't expect students to be able to have like practical manipulations. I mean, how can you impact the prices? And if you can't control the prices, what you get the best optimal bundle given the prices. We actually discovered some surprising manipulations, and the kind of interesting thing is we didn't discover the manipulations. The algorithm kind of algorithmically discovered the manipulations. So having a fast algorithm helped us kind of understand incentives better, and then we went back and made the algorithm more strategy proof. And the last thing I want to tell you about this paper is that en route, we came up with a new notion of fairness, kind of discovered with the algorithm. It's called contested envy-free. So this is kind of not necessarily about only for courses, but a lot of people here work on kind of fair stuff. So if you remember if you remember two things from this talk, maybe one of them be this kind of new notion of contested envy-free, and maybe you can use this, especially here. I think it might be relevant to this example you had where just different roommates wanted different rooms. So, allocation is envy-free if no agent prefers this another agent's allocation, and it's kind of the gold standard of fair allocation. And we have a lot of work in relaxations, but are envy-free allocations really fair? So let's look at this example. And what do you think? Would Eric want to trade cars with Muhammad?
No.
No.
Alex says no.
With two kids?
Yes,
How
kids.
much would it hurt to get the Porsche dirty, This is
It's an impractical car when you have children.
yeah. Not only it's impractical, it's just imagine getting it dirty, right? It's just,
How bad do you feel about having a dirty?
yeah,
Actually,
yeah.
so there is something even more fundamental, is that Eric doesn't want to trade kids because his kids are in the Honda. I mean, Porsches are nice, but he really loves his kids.
I feel like that's a reason to go to the Porsche, but no, I'm kidding.
And the other thing I want to tell you is that Eric's kids are cute, but only Eric wants them in his car. So Eric's kids are what I call uncontested goods. Only Eric wants them. So when we ask if this is a fair allocation, we shouldn't kind of count the kids, right? We should ask like, what's the fair allocation of cars? And then like Eric's kids should go with Eric wherever car he goes to. Okay? So if we only look at contested goods, so only cars are contested, kids are not contested. So if we only restrict contested goods, Eric still envies Mohammed's Porsche.
I would say that more than that, I mean, Eric's kids are uncontested good in the sense that they're not on the table, so to speak, right? So if you kind of look at like things like bargaining solutions and things like these are like, irrelevant. So, you have your own utility, right? And the solution should be invariant of whatever is intrinsically yours, right? Give an example.
Yes, but now I want to formalize it in the way, in the kind of bring it back to course allocation. I mean, the reason I came with this example is because the algorithm found a problem. Actually, we're analyzing incentives, and the kind of incentive issue the algorithm found were related to this issue with that we take envy freeness has becomes a very weak notion when every student has the research unit with their advisor that they really want to take, and kind of doesn't help. So kind of motivated by this example, or kind of this example is kind of, you can think of it as like an explanation. If you have this kind of competitive equilibrium, zero priced classes are uncontested, right? There is a not over demand, and it's obvious who should get them. And we want to define this contested envy if you know, Bob's schedule, Alice's schedule is better when no, if Alice contested envies Bob if Bob's schedule is better with when restricted to contested classes. Sorry for the typo, right? Like, so just like ignore the uncontested goods, look at the contested goods, see whose schedule is better, and that's how you find contested envy. And ACI happens to satisfy. So like we said, that it satisfies contested envy free if no student contested envy another student. So there's like kind of extended definition of envy, but just restricted to contested goods. And the good news is ACI satisfies contested envy free up to one class. And the other kind of fun thing is that these ideas came up from like analyzing the algorithm. So it's not like we sat, in the nice weather at Stanford and came up with these ideas. It's really kind of looking at the output of the algorithm. So algorithms and fairness and incentives all work together. Cool. So this is all what I want to tell you about the state of the art. So there's kind of, we have a practical algorithm. In theory, it's a hard problem. And there's this notion of contested envy free that hopefully you all write dozens of papers about. I want to mention a couple of directions for future work. In particular, I was/am on this committee at Stanford looking at using ACI at Stanford for the kind of undergraduate population. And I've done this kind of practical stuff before with our algorithms used in practice, but really talking to like the registrar's office and student services and actual students and so on, and hearing them, I got some like really interesting questions. Okay, so future directions. One is there are a couple of new mechanisms that you can check out and see. So Mark Raverman has this paper, like a mechanism called Apex, some kind of combination VCG and bandits with knapsack. You can read the paper, it's an archive. And there is something called efficient combinatorial assignment, which is somehow related to ACI, but also different. It's going to be a paper at this EC, so we should, those of you who can make it, can come the talk. And Alex T promised me that paper will be on archive by the actual EC conference. Another kind of really important question related to what Yair mentioned about like kind of how in Singapore they let students save the unused points from one semester to another is what happens when you go beyond a one-shot mechanism. Like a simple example is waitlisted for a class. So how should you price like spots on the waitlist? How you should price like the first spot versus the third spot versus the 10th spot? Should that also go in ACI? What if you just want to shop for class? So maybe there's like a 30% chance you're gonna keep it. How should you price that? And now this is kind of what Yair was saying. Okay, well, maybe we can balance envy now with envy in the future. Like maybe if you were on the envying side of the EF1 this semester, maybe you should be on the kind of be getting envied side next semester, and kind of maybe you can get EF1 entire degree. And then students bidding for classes, they have uncertainty about what classes they might want to take in the future. That can lead to like kind of really bad incentives. Yeah, it really kind of changes the dynamics. It makes it much harder to bid. So I don't even know how to model these. Like, what's a good model or what kind of a good theory we can hope to wide open. Another kind of last slide I have here is the question of like whether students can actually kind of efficiently express their preferences. So there's a paper at EC last year that basically lets students talk to AI, and then the AI learns preferences, and AI can bid for them in the ACI kind of like AI kind of like learns their optimal preferences. And kind of a really practical problem is that students sometimes don't know what classes they should take. Like they don't understand the degree requirements. Uh, how do they really find out what classes are good for? Oh, they kind of go to the students for the year ahead and ask them what sort of, or like the chill classes they get an A or something. But what about kind of like long term? Maybe you can use more AI to help students make those decisions. This is something that like kind of at Stanford, I know some of the admins really wanted is a system that helps students understand their degree requirement and like figure out what classes to take. They're like, this is a much higher priority than kind of like higher utility or whatever you economists call it. So very interesting questions. So just to wrap up, I told you about ACI. I told you about this new notion of fairness, contested, envy-free, right? Should Eric envy Muhammad? The kids are uncontested. And some very interesting opportunities for future work on fair scores allocation. So that's it. Thank you. And thanks, Alex and Yair, for organizing. Thanks, everyone, for coming.